Hello friends, welcome back. In our next section, we are going to discuss about layer 3 routing within virtual extensible LAN, and in particular, we will look at how symmetric IRB and asymmetric IRB works, and we will also look at it from a configuration point of view. So friends, with integrated routing and bridging, a VTEP performs both switching and routing function, i.e. it performs a lookup in the MAC address table. It also performs an IP routing lookup. It then rewrites the layer 2 frame and then forwards the packet to its next hop. So with inter VxLAN routing, we can have a host in a particular VNI, for example, VLAN 10 or VxLAN 10,010, route a packet to another host in a different VNI without having the VTEP to maintain the same MAC address table or ARP entries on each device. Hence the term integrated routing and bridging. It is analogous to inter-VLAN routing from a classical Ethernet point of view. So in this section, we will look at integrated routing and bridging or IRB from a BGP EVPN standpoint. So with BGP EVPN, we have two options for integrated routing and bridging. So we have asymmetric IRB and then we have symmetric IRB. So friends, let's discuss about asymmetric IRB first, and then we'll have a look at how symmetric IRB works. So with asymmetric IRB, the ingress VTEP does both a layer 2 and a layer 3 lookup. So the ingress VTEP receives the layer 2 frame in its local VNI. It routes the packet locally to the destination VNI, and then it bridges the packet across to the destination VTEP, whereas the egress VTEP only does a layer 2 lookup. Hence the term bridge route bridge. So let's understand this from a traffic flow point of view, which will make things clearer. So here we have a very simple topology which consists of 3 servers and 3 leaf switches connected to a couple of spine switches upstream. These leaf switches are also acting as the default gateway for the servers. Also in our topology, we have server 1 in VLAN 10 and server 2 in VLAN 20. So now if server 1 wants to communicate to server 2, and as they are in two different VLANs and two different subnets, server 1 will have to send any packet towards server 2 first to its default gateway, which is leaf 1 in our example. And in terms of the IPs, server 1 has an IP of 192.168.10.101, and server 2 has an IP of 192.168.20.102. Now, if server 1 wants to communicate with server 2, it will first perform a logical AND between its IPN mask against the IPN mask of server 2. Again, that is normal Ethernet logic and has nothing to do with VxLAN. So it will first of all send the packet towards its default gateway, which is leaf 1. So this packet will have a source IP of server 1, destination IP of server 2, source MAC of server 1, and destination MAC of leaf 1. Leaf 1 will now say its own MAC address in the destination MAC field of this packet, and then it will know that the packet needs to be routed. Leaf 1 would already have a MAC entry for server 2 from a BGP EVPN advertisement by leaf 2. So when server 2 comes online or it sends any traffic, be it a gratuitous ARP towards its default gateway, leaf 2 in this example will generate a BGP EVPN route type 2, and since it is pairing with spine 1 and spine 2, leaf 2 will send that route type 2 towards the spines, and as these spines are configured as route reflectors, we'll send that update to the remaining leaves. So leaf 1 will have already received a MAC and host entry. Again, the host entry is optional, but it would have received a MAC entry for server 2 via spines, and it will know that to send traffic to server 2, the next hop will be leaf 2. So leaf 1 will now encapsulate this packet that it previously received from server 1. So leaf 1 will encapsulate this packet in the VNI for VLAN 20, which it would need to have configured locally. And for the source IP of this encapsulated packet, it will use its own IP address that we have configured in the NVE interface or the VTEP interface. And the destination IP would be the NVE or the VTEP interface for leaf 2. And lastly, it also needs a source and destination MAC for transporting this VxLAN encapsulated packet towards the spines. So the source MAC would be the MAC address of the interface pointing towards one of the two spines depending on how the traffic gets hashed. And the destination MAC address would be the MAC address of the next hop, which would be one of the two spines. So let's say spine 1 in this example. Spine 1 will then receive this packet. It will see its own MAC address in the Ethernet frame, and then it will know that the packet needs to be routed. So it will see the IP address of leaf 2 in the destination IP field, and then it will send that packet towards leaf 2 after rewriting the source and destination MAC. So the source MAC will now be the MAC address of the interface facing leaf 2, and the destination will be the MAC address of the interface on leaf 2. So when this packet gets to leaf 2, it will see its MAC address in the destination MAC address field. So it will decapsulate that frame. It will see its IP address in the destination IP of the VxLAN encapsulated packet. It will further decapsulate that packet. It will then see that it's destined to VNI 20, which it has configured locally, and that VNI maps to VLAN 20. And then it can bridge that packet locally, that is towards server 2. So from a configuration point of view, we have server 1, which is in VLAN 10 with an IP of 192.168.10.101. And then we have server 2, which is in VLAN 20 with an IP of 192.168.20.102. And then we have leaf 1, which is configured with an SVI of 192.168.10.1 for VLAN 10. And then we have an SVI for VLAN 20 on leaf 1 with an IP of 192.168.20.1. So we have VLAN 10 and 20 configured on leaf 1. It is configured under VRF 10 and 1. Likewise, we have the same configured on leaf 2. So we have IPs of 192.168.10.2 in VLAN 10 and 192.168.20.2 in VLAN 20 configured respectively on leaf 2. So let's check the reachability between server 1 and leaf 1 and server 2 and leaf 2. So yeah, server 1 can ping its default gateway, which is 192.168.10.1 configured on leaf 1 SVI for VLAN 10. Likewise, server 2 can ping its default gateway, which is 192.168.20.2, which is configured on VLAN 20 on the device leaf 2. So now let's check if server 1 and server 2 can ping each other. So server 2 has an IP of 192.168.20.102. So yeah, we lost a couple of pings. That is expected. So now yeah, we see server 1 can ping server 2, and let's have a look at the Wireshark capture to understand the encapsulation. So from a traffic flow point of view, any traffic that gets into leaf 1 and it is destined to leaf 2, it can either go in the direction of spine 1 or in the direction of spine 2. So we are running a capture on the link between leaf 1 and spine 1, and we have captured a few packets. So let's have a look at the Wireshark captures. So if we look at one of the captured packets, so we have the original payload, that is the original packet with an IP address of 192.168.10.1 as a source and 192.168.20.102 as a destination, which are server 1 and server 2 respectively. So leaf 1 received this packet on its VLAN 10 interface. So it will check the destination IP, and as it has an SVI configured for VLAN 20, leaf 1 will now encapsulate this packet with its own router MAC, which is this value here, and with the MAC address of the destination host, because leaf 1 already has an entry for server 2 in its ARP entry. So this packet now gets encapsulated with the VxLAN header. And as we see, the packet came in on VLAN 10, then it got routed to VLAN 20 as we see on the Wireshark capture. So the VNI value is that of VLAN 20, which is 10020. Leaf 2 will decapsulate this packet. It will see it is VxLAN encapsulated with a VNI value of 10020, which is mapped to VLAN 20 locally. It has a destination MAC of this value, which is 0210, and Leaf 2 already has that entry in its ARP cache, and it will then forward that packet towards server 2. The drawback of this routing method is that for the return traffic, the roles are reversed, which means that leaf 2 now becomes the ingress VTIP and leaf 1 will be the egress VTIP. This means that for the return traffic from server 2 to server 1, when the packet hits leaf 2, for it to be able to route the traffic locally, it needs to be configured with VLAN 10 or more specifically SVI for VLAN 10 and then bridge that packet across to leaf 1 where the traffic will be bridged locally towards server 1. So when the packet flew from leaf 1 to leaf 2, it was encapsulated with a VNI value of 10020, which is the destination VLAN to VNI mapping, and when the return traffic came from leaf 2 to leaf 1, it was encapsulated with a VNI value of 10010, which is the mapping between VLAN 10 and VxLAN. So as the egress and ingress packet have different VNI encapsulations, hence the term asymmetric IRB. And as you might have noticed that with asymmetric IRB, we need all the VLANs and all the SVIs for which we are routing. They need to be configured on all the leaves, which means that all the leaves will need to maintain a MAC address table for all the VLANs and their ARP entries as well, which from a configuration perspective could be simpler, but from an operational and performance point of view, it is not very scalable. So friends, let's now discuss how symmetric IRB works in the scope of BGP L2VPN EVPN. So with symmetric IRB, both the ingress and egress VTIPs perform both function, i.e. layer 2 and layer 3 lookups. Hence, symmetric IRB is also called bridge route bridge method. So with symmetric IRB, we have a new concept called a layer 3 VNI, which is a shared VNI between all the VTIPs. So each tenant VRF is mapped to a unique layer 3 VNI, and this mapping must match on all the VTIPs. So all VxLAN routed traffic is encapsulated within this particular L3 VNI in the VxLAN header. So using this unique layer 3 VNI, all the VTIPs can now route traffic without needing to create VLAN to VNI mapping on all the VTIPs and maintaining the MAC address and ARP entries for all the VLANs or specifically VNIs. So let's understand the symmetric IRB packet flow using the same diagram that we used for asymmetric IRB. And once we go over a packet walk, things will be much clearer. So we have the same topology where we have 3 leaf switches connected to 2 spines in a cloth topology. And then we have server 1 connected to switch 1, and then we have server 2 connected to switch 2. So leaf 1 and leaf 2 are the default gateways for server 1 and server 2 respectively. And here server 1 is a member of VLAN 10 and server 2 is a member of VLAN 20. And from a config standpoint, VLAN 10 is mapped to VN segment 10,010 and VLAN 20 is mapped to VN segment 10,020. But with symmetric IRB, we now configure a unique layer 3 VNI. And in our example, we are using the value 50,000. So we configure another VLAN to VNI mapping on all the participating leaf switches. So as we can see, we have configured VLAN 500 mapping to VN segment 50,000. And if we check the VRF configuration, So we map the VNI 50,000 to VRF tenant 1 in our example, and this mapping must match on all the VTIPs. So from configuration standpoint, we must first create the VLAN and then map it to a VN segment, or that's the VLAN to VNI mapping. And then we map that new layer 3 VNI with the VRF. So this is the layer 3 VNI which is associated with this particular VRF. And this VNI will now be used to carry routed packets between the ingress and egress VTIPs. And we will also need to create an SVI for this VLAN using the IP forward command. And this command allows the MAC address to be rewritten without the need to change the layer 3 header. And finally, we need to go under the interface NVE1 on the VTIPs and associate the VNI with the VRF using the member VNI associate VRF command, as we see on the screen. So with Symmetric IRB, there is no need to create the VLAN to VNI mapping or the SVIs for all the VLANs on all the participating VTIPs. So as we see, Leaf 1 only has an SVI for VLAN 10 configured. Similarly, Leaf 2 only has an SVI for VLAN 20 configured locally, because Leaf 1 only has access ports configured in VLAN 10 and Leaf 2 only has access ports configured in VLAN 20. So now if I ping from server 1 to server 2, which are on different VLANs behind different VTIPs, so let's say if I ping 192.168.20.102, which is the IP address for server 2 in VLAN 20, which is behind leaf 2 from server 1, which is in VLAN 10 behind leaf 1. So let's see if that works now. So yeah, we can ping, and let's take a quick look at the Wireshark packet capture. So we ran another ping from server 1 to server 2, and we got some captures as we see. So let's take a quick look at the Wireshark capture. So here we have the ICMP payload, which is an echo request with the source IP of the inner IP header being the server 1 IP address as a source and the server 2 IP address as the destination. For the source and destination MAC address of the Ethernet header, Leaf 1 will use its router MAC as the source, which we see here, and it will use the router MAC of the destination VTIP, that is leaf 2 in our example, as the destination MAC address. And on leaf 1, if we check the BGP EVPN routes it has learned from the spines, we see that it has received the 192.168.20.0/24 route. So that's the subnet mask and that's the actual IP prefix, with the next hop being 2.2.2.2, which is the VTIP IP address of leaf 2. And leaf 2, when it sent this Type 5 update towards the spines, which are the root reflectors, it also sent its router MAC address, which is used as the destination MAC address of the inner Ethernet frame, like we see here. And then this packet gets VxLAN encapsulated. So we can see that the VNI value that this VxLAN encapsulation is using is the value of 50,000, and that is the VLAN to VNI mapping that we created earlier. So as we see, the VRF tenant 1 is mapped to VNI value of 50,000. And if we now check the return traffic from leaf 2 back to leaf 1. So here we have the ICMP reply packet. So that's the ICMP payload, which is an echo reply. The inner IP header would have the source IP address of server 2 and the destination IP address of server 1. It will have the source MAC address of leaf 2 and the destination MAC address of leaf 1. That is the router MAC, which is exchanged as part of root type 5. And the VxLAN header uses a VNI value of 50,000. This is where symmetric IRB is different from asymmetric IRB. With asymmetric IRB, we use different VNI values for outbound and inbound traffic, but with symmetric IRB, the VNI value remains the same, hence the term symmetric IRB. And for the outer IP header, we use the source MAC address of the VTIPs. we use the source IP address of the VTEP, so leave 2 as the source IP address and leave 1 as the destination IP address. And then we have the outer Ethernet header, which uses the MAC address of the interface connected to one of the spines depending on the load balancing algorithm or the hashing. And then it will have the destination MAC address of the other side of this link, i.e. the interface on the spines. So just to summarize the steps that we take in the packet walk between the VTEPs when using symmetric IRB. So both the ingress and egress VTEPs will route the packet to its final destination. The ingress VTEP routes the packet to the final destination with the egress VTEP as a next hop. And after the egress VTEP performs the decapsulation, it does a routing lookup to decide the path to the final destination. And lastly, the VNI used to carry the packet between the ingress and egress VTEPs is a unique or a common layer 3 VNI that is associated with a VRF, like we saw in the configuration section. So friends, in this session, we had quite a detailed look at how symmetric and asymmetric routing works as far as BGP, L2VP, and EVPN is concerned. We also performed packet walk for both the routing methods. So that's it for this session. I hope you liked this video. And if you did like the content, please like the video, subscribe to my channel, and I welcome all comments, good or bad. Please feel free to share your feedbacks. I really appreciate the time you've taken to stop by today, and until next time, thank you very much.